The evolution of flight is a great example of the mechanisms by which evolution works. The ability to conquer the air, the ability to utilize airspace is really important in terms of the success of different organisms. And remarkably, this is a feat that has been achieved multiple times through evolutionary history. Let's start off with looking at the types of flight, and then we'll look at some of the details of flight itself. So one of the things we want to start off with is what are the approaches to being airborne? And one of the approaches is passive flight. So passive flight means that you're a relatively small organism. When you're small, that means that the relative thickness or relative viscosity of the fluid medium you're in, be it water or air, is thicker the smaller you are. So if you're incredibly small, you go back to the average diameter of a microbe being 1 micron in diameter. When you're that size, then everything you're in, be it water or air, is extremely thick in a relative sense. So passive flight is the idea of organisms being extremely small and being suspended within these very relatively thick media called water and air. The next one is gliding flight. And gliding flight is where simply you have a wing structure that's not being flapped or moved, but it is a wing structure that's stable, and it allows you to be buoyed up on, in the case of air, on masses of air that have different temperatures, or of course if you're in the water, you can glide through the water. Then the last one is powered flight, and powered flight is kind of the one that we think of the most when we say flight, and that is of course when you have muscular control over your wing structure, and allows you to have great adaptability and motility as you move through the air, or in the case of the water. So the one thing that we need to remember though in these three versions of flight is that the last one, the powered flight, is the one that takes a lot of energy. And so organisms who develop powered flight have made trade-offs, and they've had to devote a lot of energy in their life history towards that flight mechanism. Now, if we look at flight as it pertains to birds, which is a combination of powered flight and gliding flight, one of the kind of interesting ideas is, well, how did the Saurischian carnivorous theropods evolve eventually in the Mesozoic from being dinosaurs into Archaeopteryx, the link between dinosaurs and birds, and then eventually become birds? And so that transition is thought to have occurred in a couple different ways. One is called the arboreal hypothesis, and that's the idea of the dinosaur jumping out of a tree. But you know, jumping out of a tree, there aren't a lot of intermediate stages. Either you can jump out of a tree and survive, or you don't, and it's not that widely accepted. Another one is called the cursorial hypothesis, and that's the idea of, well, maybe flight developed as a non-intended consequence of doing things like running on the ground. So small raptors that might have been chasing organisms that they were trying to prey upon, as they were moving and jumping and running and going after their prey, then the idea there is that you could have had that transition into some type of a flight mechanism. If you added feathers, again, probably for keeping thermal regulation as the primary cause, added feathers to this organism that was running and jumping, the raptors, then it might not have been too much of a stretch to then start the flight process in that way. So there are a lot of different ideas about flight, but we think that this cursorial raptor running hypothesis is kind of the one that we'll stick with. Now, flight itself, if you look at the mechanics of flight, there's two kind of end-member camps on this. One of them is called the Bernoulli principle, and that's the idea that as you increase the velocity of a fluid, again in this case let's talk about air, as you increase the velocity of a fluid over a wing structure, then the increased velocity fluid, the air, has a lower confining pressure. In other words, it has a lower pressure the faster it goes. So the cross-section of a hydrofoil or a wing structure has a relatively flat bottom and a convex upward shape. And what that shape does is, as the wing moves laterally through the air that moves under the wing is relatively the same speed as it was before the wing structure got to that air. But then as the air moves over the top of the wing, it has to accelerate to cover the same distance as the air under the wing. So that acceleration causes a decrease in pressure, and the wing lifts. The other alternative or additional aspect of this is that every time a wing foil moves through air, the air actually sticks to the surface. So there's a very, very tiny layer called the boundary layer, where the air itself is actually sticking to the wing, and it has no velocity. And then as you move up off the top surface of the wing, just very, very small distances, angstroms to nanometers, then you transition into increasing flow. But right at where the air touches the wing, there is no motion. So this creates a boundary layer effect. And the boundary layer results in having the air on the top of the wing actually stick to the wing. You move up from the wing, you increase the velocity. That does have a decrease in pressure. But then as the air moves past the wing, then it'll be forced downward. And so the ability to fly and the engineering that goes into building modern day wings is a combination of these kind of two effects. The decrease in pressure caused by increased velocity, allowing us to have lift, and then the idea that the Coanda effect and the boundary layer conditions actually create a turbulence that comes off the back of the wing.